In this chapter, we will be introducing the concept of integration. In this lesson, we'll be looking at trigonometric substitution.
Okay, hi everybody. So today we're going to take a look at something called trigonometric substitution. And this is just another way of helping change complex integrals into something that's a little easier to handle. Now, what trigonometric substitution allows us to do is we get to replace binomials, okay, in an integral here. And the binomials we're going to look at here, we're going to be able to replace a squared plus x squared, okay, assuming that a is some sort of a constant here and x is our independent variable. We're also going to be able to look at a squared minus x squared and x squared minus a squared. Okay, and there is a significant difference there, and you'll see how that works out in just a second here. And what we're going to do is the substitutions that we recommend for this is interesting here, and we've seen this pattern before. We're going to take these two terms here, and we're going to represent these two squared terms here by a single squared term, and we do that by using trigonometry. And the substitutions that we recommend here are going to look like this. We're going to let x equal possibly a times the tangent of theta, or we're going to let x equal a times the sine of theta, or we're going to let x equal a multiplied by the secant of theta, to get rid of these binomials. Now that looks a little weird right on the face of it, but actually it makes a lot of sense once you kind of break this down. So just to give you an idea of what's going on here, let's say that we are going to use this as our substitution here. Okay, and I'll show you an example of how this works in just a moment here, but let's take a look at what this is saying. Okay, so if we allow x to equal a tangent of theta, okay, then really what this is saying here is that the tangent of theta is equal to x over a. Okay, no big surprise there, you're aware of that. But let's put this in a different context. Let's take a quick look at that triangle that's being described here. Here's our right angle triangle. If this is theta, okay, tangent is opposite over adjacent. And when we put those together and we use the Pythagorean theorem to get the hypotenuse, we're going to get that the hypotenuse is the square root of a squared plus x squared. Well, there it is. There's that binomial popping out up there, that a squared plus x squared. So now there's this little link between tangent, okay, and that expression right there. It's still part of that triangle. Here, if we were to use x is equal to a sine of theta, well, what this is telling us is that the sine of theta is going to equal x over a. And once again, let's take a quick look at what that triangle looks like. So if here's theta, x is the opposite. Now in this case here, a is going to be the hypotenuse. So let's use the Pythagorean theorem to figure out what the adjacent side is, and that's going to be a squared minus x squared. Okay, the square root of a squared minus x squared. And then again, you'll see that little pattern pop up, that binomial. Now, at this point here, it probably isn't making a whole bunch of sense because you're looking at the tangent here, and look, I don't need the hypotenuse to get the tangent here. But let me show you, let me draw out the last triangle here. Then I'm going to go back and we're going to do a quick substitution here, and I'll show you why this works, okay? So here, what we're being told here is that the secant of theta is going to equal x over a. And again, let's draw the triangle. And so here's our right angle, here's our theta. Now, if secant is x over a, that means that in this case here, the hypotenuse is x and the adjacent side is going to be a. And then by using the Pythagorean theorem, I see that the opposite side is going to be x squared minus a squared. And again, there's that binomial we had mentioned a little while ago. Now, how does this work? How do these substitutions, I mean, we see a link clearly to the binomials up here, but how do those substitutions make any kind of a difference whatsoever? Well, let's just take a quick look at the first one here, at x is equal to a tangent of theta. So I'm just going to change colors here. Let's say that we have got this expression right here, just for an example here. Let's say that in our integral we see an a squared plus an x squared. Okay? And now we're going to make the substitution here. We're going to let x equal to a tangent of theta. So that means this is going to become a squared plus a tangent of theta squared. Okay, well, let's distribute the square. That's not a big deal. So it's going to be a squared plus a squared tangent squared of theta. Okay, well, notice in this expression we've got a common a squared, so I can just factor that out, and I'm left with 1 plus the tangent squared of theta. And now here's where we're going to see the magic happen, because 1 plus the tangent squared of theta, think back, that's an identity. And so now I can replace that with, make this a squared multiplied by the secant squared of theta. And that's what we were looking for. So now this binomial with two squared terms in it becomes a monomial that's being squared. And that is often a whole lot easier to work with. Okay, so that's what we're going to do. We're going to use these substitutions here with trigonometric functions to take these binomials and convert them into monomials that are being squared so that we can hopefully simplify down the expression in an integral and make it easy enough to do without too much effort here. So let's take a look at some examples just to see how this works. Okay, so in this example we're being asked to evaluate the integral of 1 over x squared multiplied by the square root of 1 minus x squared dx. So x is the independent variable here, that's what that means. Okay. Now, when I see that square root of 1 minus x squared there, I think back to these triangles that we've set up here, and I recognize that same pattern right here when I let sine of theta equal x over a. Okay. Now, to compare that to my expression right here, notice that the a is 1. So what I'm going to do here is I'm going to do the substitution here. I am going to let x just be the sine of theta. Okay? Now, with the stipulation here that theta is going to be restricted, okay? Theta is going to be between negative pi over 2 and pi over 2. Now, just to be clear as to what I'm doing right here, there is a restriction implied in this expression right here. Notice that, and I'll change my change the color here. Notice that my domain here, because of the radical down here, it's going to be that x is going to have to be greater than negative 1 and at the same time less than positive 1. Okay? Now, that implies, and maybe not or equal to here because of those endpoints there, but certainly I'm going to, and actually I will do that, I'll get rid of the endpoints there. If you plug negative pi over 2 into theta right here, you'll get negative 1, and if you plug positive pi over 2, you'll get positive 1. So I'm letting my angle go between negative pi over 2 and pi over 2 to give me values between negative 1 and 1 for x here. Now, having done that, if I take the derivative of that with respect to theta, I will get cosine of theta. So my dx here will be the cosine of theta d theta. Okay, now additionally, and I'll maybe do this over here, when I make that substitution that x is equal to sine of theta, what that means down here in this radical is that my radical, the square root of 1 minus x squared, is going to be equal to the square root of 1 minus sine squared. Now, that's actually really convenient because I know that 1 minus sine squared is the same as cosine squared thanks to a trig identity. Okay? And then I'm going to be able to take the square root of that and get the cosine of theta. Now you might look at that and wonder, well, wait a minute, can I get away with that? I mean, granted, I'm squaring the cosine and the square root will cancel the cosine, but in that domain, you know, is that equal? Is cosine, because remember, this is always going to produce a positive value. The square root of a square is going to produce a positive value. is cosine always positive in the domain that I'm given? And yes, it is. Okay, bear in mind that this right here, we're talking about this part of the curve here. And in these two quadrants, cosine is going to be positive. So actually that works out just fine. I am okay with that. So now when I do this substitution, my original function is going to become, I'll come down here, okay, is going to become the integral of, and what have I got here? I am going to have cosine of theta over the sine squared of theta cosine of theta d theta. Now just to explain all those parts there, just in case something doesn't quite make sense there. First of all, the x squared up here, if I let sine of theta be x, then that's going to be my sine squared. I just figured out that the square root of 1 minus x squared is going to be cosine of x. That's this little bit right here. And when I got rid of the differential, the dx, remember dx was equal to cosine theta d theta, so that's this little bit right here. And that's wonderful because I know that the two cosines will cancel, and so this is going to become the integral of 1 over sine squared theta d theta, and that is the integral of the negative, I'm getting ahead of myself. I already know there's a negative that's going to pop out of this, but we're not there yet. So let me just get rid of that. It's going to be the integral of cosecant squared theta d theta, and I have done nothing. Whoops, sorry. I have done nothing there. I've just rewritten 1 over sine squared as cosecant squared. That's just naming it here. But I know what the answer to that is. Okay, because I know my derivatives here, and I know that the derivative of cotangent or negative cotangent will be cosecant squared here. So this is going to actually be the negative cotangent of theta. And because it's an indefinite integral, plus c. Now that's pretty awesome. So I've got it down to expression. I've actually evaluated the integral here. Except for one fairly glaring issue. The variable here is theta, but in my original problem, the independent variable is x. So what I need to do is I need to change this so that the independent variable is x. But that's actually really easy to do. And I can do that by actually sliding back up to those triangles up there. Okay? Because remember, this is the information that I used. I let sine of theta be x over 1. At least in this problem, a was equal to 1 here. So it gave me this triangle right here when I tried to interpret that information here. Now, what would cotangent look like? Well, cotangent is going to be the adjacent side to the angle divided by the opposite side. So this is going to end up being the square root of, in my case here, 1 squared minus x squared over x. So coming back down to this is going to equal the negative square root of 1 squared, which is just 1, minus x squared over x plus c. And so that's the solution. So let me write this out again over here just to maybe make sure that it's clear what I'm doing here. 1 over x squared square root of 1 minus x squared dx is going to equal negative square root of 1 minus x squared over x plus the arbitrary constant at the end there. And that should give you a sense of how trigonometric substitution works. But I'll show you another example here. Okay, so in this example, we're being told to evaluate the integral of basically 1 over the square root of 4 plus x squared. Now, if you flip back to the triangles that we looked at before, okay, the square root of a squared plus x squared, this is the pattern that we're seeing, and this is the substitution that we're supposed to use. We're looking at a tangent here. Now, in the specific problem that we're looking at, because it's 4 plus x squared, clearly the a is going to be 2. So, coming back to our question here, the substitution that they're hinting at here would be that x will equal to 2 tangent of theta. Now, we're going to introduce a restriction here on the variable theta. We're going to let theta go from negative pi over 2 out to pi over 2. And actually, once again, I did it again. I shouldn't be including the or equal to there. Whoops. And I'll explain that by saying this. When you think about tangent, okay, you think about the graph of tangent. Out here at negative pi over 2, there's an asymptote. Out here at positive pi over 2, there's an asymptote. And then tangent looks like this. Kind of like a squished together little cubic. But notice that between negative pi over 2 and pi over 2, the tangent function takes on all real values. So although it looks like I'm restricting the domain here, okay, it turns out the range, okay, the values for x here are going to be unlimited. So this is a great substitution here. Now when I take the derivative of this, dx by d theta, okay, I am going to get 2, and the derivative of tangent is going to be secant squared theta. So dx will equal 2 secant squared theta d theta. So I've got this part of my substitution. Additionally, notice that when I plug 2 tangent of theta in for x in the expression here, that, I'll maybe make a little comma here, that we get the square root of 4 plus what will end up being 4 tangent squared of theta. And you can factor out, this little bit here, you can factor out the 4 and you get 1 plus the tangent squared of theta. And just like in our previous example, that's an awesome thing here because 1 plus tangent squared of theta is just secant squared theta. And so once again, I take that binomial with the square in it and I reduce it to a monomial that's being squared. So now if I put these pieces into the integral here, now let me start this again here, the integral of the square root of 4 plus x squared dx will be the integral of, okay, well dx, I just discovered up here, dx was equal to 2 secant squared theta d theta over, and then I just did my substitution over here, so I know that that denominator is going to be the square root of 4 secant squared theta. Okay, now this is going to become, okay, the integral of, well, okay, now watch this. The square root of 4 is going to be 2, and the 2's will cancel. So then I'm going to be left with the secant squared of theta, d theta, over, and now I've got the square root of secant squared, which will be the absolute value of the secant of theta. Okay? And that's, if you're not sure about that, you can go look that up online there and you'll see explanations of that. And anytime you take the square root of the square of something, really what you're looking at is the absolute value of it. Now, this works out totally fine though, because remember that I restricted my domain from negative pi over 2 to pi over 2. So if we think about that in terms of the coordinate plane, I'm talking about these two quadrants right here. Well, cosine is positive in those two quadrants. And so as a result, the secant is going to be positive in those two quadrants. And so the absolute value here, although they pop out because of the definition of the square root and whatnot, yeah, turns out it's not an issue because it would have been positive anyway. So I can actually make a cancellation here, and this is going to end up being equal to the integral of secant theta d theta. Now, at this point right here, I'm actually going to take the opportunity, we're going to take a quick look at an interesting little integral here. This is an interesting little beast unto itself here. Now, what I'm about to do here isn't really trig substitution. It's more just a trig integral here, but it's kind of neat. And it's worth kind of taking a quick look at here because it might not be abundantly obvious what the integral of the secant of theta d theta is supposed to be. Now, what I'm going to do here to help me evaluate this is I'm going to actually insert an expression here that's going to make this possible. And again, bear in mind that I used trigonometric substitution to get to this point. This is now going to be, I guess, a little aside. I'll maybe put a little note here. This is an aside just from the trig substitution that I'm doing, just to do this integral right here. So what I'm going to do is I've got this secant theta here. I'm going to multiply it by 1. But I'm going to multiply it by a very special looking one. Secant theta plus tangent of theta over the secant of theta plus the tangent of theta, d theta. Okay? Now, I'll be honest, this isn't my idea. Okay, this would very likely not have occurred to me, not for a very long time. But I can appreciate the genius of it when I see it. That's really, really clever here. Because watch what happens when I expand out that numerator. I get secant squared theta plus secant theta tan theta. This is all over secant theta plus the tangent of theta, d theta. Now, maybe at this point, you're not quite clear on what is it that makes that so clever. Well, here it is. All I did was multiply by 1. Now, that's a kind of an odd looking one, but it's just 1. That's equivalent to 1 here. Now, with this integral, what I can do is I can introduce a new variable here, what I might call the dummy variable. And I'm going to let u equal secant of theta plus the tangent of theta. And when I take the derivative of u with respect to theta, well, the derivative of secant theta is going to be secant theta tan theta, and the derivative of tan theta is secant squared theta. Well, that's outstanding because that's the numerator. So here, when I make my substitution, what I do here is I'm going to take my du over secant theta tan theta plus secant squared theta, oops, and that's going to equal my d theta. Now, maybe what I'll do here is I'm gonna move this over to the side here so that you can see this a little bit clearer. So I'm going to come back up here, and this is going to now equal the integral of secant squared theta plus secant theta tan theta. And this is now going to be du all over u multiplied by secant squared theta plus secant theta tan theta. And these two expressions right here will cancel, and I'm going to be left with just the integral of 1 over u du. And that's amazing. It's amazing that that works out as beautifully as it does, because this now becomes the natural log of the absolute value of u plus c. Okay? And now I take that back because I know what u is. U is, okay, secant theta, whoops, I forgot the c there. Secant theta, I'll write that again. Don't like the way that looks. Okay, that's going to be secant theta plus the tangent of theta plus the all in absolute values there. Now, let's flash forward to the question that we've been working on. Now that we've got it down to this, and maybe what I'll do is I'll come back over here. So now I know that my integral is equal to the natural log of the secant of theta plus the tangent of theta, okay, plus c. This is the point here where I remember that my independent variable isn't actually theta. Remember, it is x. The original problem, if I slide way back up to the top here, the independent variable in my problem here is x. But what I can do here, based on the substitution that I did, okay, I let x equal the tangent of theta. I let x equal 2 times the tangent of theta. My mistake. Sorry, I forgot about the 2 there. So tangent of theta is equal to x over 2, which means if I draw that triangle, tangent of theta is going to equal x over 2. That makes the hypotenuse here the square root of 4 plus x squared. Okay, so this is where I got this. This is the triangle that gave me the trig substitution piece that I used here. So that's also going to give me the way of interpreting this. So my natural log here, instead of having a secant in it, well, what would secant be? Okay, well, secant is going to be the hypotenuse over the adjacent. So this is going to be the square root of 4 plus x squared all over 2. And the tangent is going to be x over 2 plus c. Okay? So here's our expression. And actually, we can play with that a little bit if we wanted to, but you know what? That actually is really good the way it is. So I'm not going to actually go any further than that. I know that I can do a little bit because of the division here. Well, shoot, maybe I should. Okay. Let me write it like this. As soon as I say it, I think, maybe I should just do it. So this becomes 4 plus x squared plus x. This is all over 2. And if you think about your laws of logarithms, okay, this is going to be the same as the natural log of the square root of 4 plus x squared plus x minus the natural log of 2 plus c. Now, because the natural log of 2, subtract the natural log of 2, because that's just a constant, really, this is just now the natural log of the absolute value of the square root of 4 plus x squared plus x, and then I might just add, I don't know, another c or a c primed here, just to indicate maybe that it's a different c than this. But I'm just going to include that natural log. Basically, when you take an arbitrary constant and add a constant to it, what you get is an arbitrary constant. Okay, so wow, that took a while here. If we kind of zoom out on this one, that's a big problem there. Look at that. All right, man, you really do feel like you worked for that one. Okay, and there you go. Okay, I want to do just one more example with you of trigonometric substitution. So the question is here, evaluate the integral of x squared dx over the square root of 9 minus x squared. Okay, and I recognize, again, this as being that sign substitution. This is like the first question that I did. But in this case here, the a value is going to be 3, right? Because this is my a squared minus x squared. So what I'm going to do here is I'm going to let x equal 3 sine theta. And the domain that I'm going to be working with, just like before here, will be negative pi over 2 theta out to pi over 2. And remember that covers everything that I need. When you take a look at this right here, the domain right here is going to be negative 3 to 3 anyway. And if you plug this domain into your expression here that I'm using to substitute, you'll get the same thing. I'll go from negative 3 to 3. Okay, so now let's take the derivative. So dx by d theta is going to be 3 cosine theta d theta. Whoops, sorry, I'm getting ahead of myself. That's what I'm going to do next. Okay, so 3 cosine theta, and so dx is going to equal 3 cosine theta d theta. Now, I also know, because of the substitution that I'm choosing here, this x, I know that 9 minus x squared is going to be 9 minus 3 sine of theta squared, or 9 minus 9 sine squared of theta. There's a common 9, so I can factor that out. And 1 minus sine squared of theta is cos squared. Okay, and so there we go. So my substitution works us down to here, and I get this cosine squared. In a little bit, we're going to see that once again, the fact that it's cosine actually works in our favor, particularly with our domain that we're using. So now I'm going to make the substitution. So I've got my integral of x squared dx over the square root of 9 minus x squared, and this is going to become the integral of, well, my dx, okay, my dx was this 3 cosine of theta d theta. Oh, sorry, I forgot about the x squared up there. If I plug 3 sine theta into the original problem here, the 3 sine theta into this x, I will get 9 sine squared theta, sine squared theta. Then I'm going to substitute my dx in, and I'm going to get an additional 3 cosine theta d theta. And I already know that the denominator is going to end up being the square root of 9 cosine squared of theta. Okay, well, let's have a look at this. This is going to be the integral of, what is that? It's going to be 27 sine squared theta cos theta d theta. Square root of 9 will be 3. And remember that the square root of cosine squared will be the absolute value of the cosine of theta. But that absolute value is actually not an issue here, because let's go back to the domain that theta is in. Theta is working from negative pi to negative pi over 2 to pi over 2. So that puts it in quadrants 1 and 4. And we already know that cosine is positive in those quadrants. So I don't even really need the absolute values here. And what's going to happen is the cosine is going to cancel, the 3 is going to cancel, and we're going to be left with the integral of 9 sine squared theta d theta. All right. So I was wonderfully able to transform this equation with its binomials and the squares and the square in the numerator to this beautiful little trigonometric integral. Okay, so now I'm going to take the 9 out because it's a constant, so I need to worry about it. But sine squared, okay, what do I do with sine squared? Well, I remember my identities. Now, don't make that 1 minus cosine squared. Okay, that's maybe not going to take you the direction you want to go. You're going to end up doing a little loop there. But I do know that sine squared is equal to, well, let me write the identity this way. I know that the cosine of 2 theta is 1 minus 2 sine squared of theta. I know that relationship. So I can get that sine squared of theta out of that by making this 1 minus the cosine of 2 theta all over 2 d theta. And actually, this is why I wanted to do this question with you guys, because I wanted you to see what happens here. Because now that 2 is going to distribute to both of those terms here. And when I take the integral, now that 9, I'm going to be stuck with that 9, so not a big deal here. In fact, I might even take the 1/2 out, so we'll make that 9 over 2. And then what I'm going to get here is the integral of 1 d theta is going to be theta, and the integral of negative cosine of 2 theta is going to be negative sine of 2 theta over 2. And then plus c. Remember, you got to remember the arbitrary constant. Don't ever forget that arbitrary constant. Okay. Now, what's really unique about this is that that theta popped out all on its own without a trig function there. And I want to show you how you deal with that when you're working with a trig substitution here. I'm going to show you how this kind of informs how we answer this question here. So now, what we're going to do here is I'm going to make this a little bit easier for myself here, because I don't really have a nice clean way of dealing with sine of 2 theta. So what I'm going to do is I'm just going to use an identity, okay? And I know that the sine of 2 theta is going to be 2 sine theta cos theta, and this is still all over 2, plus c. Well, I know the 2's will cancel, and I'm very happy that they do. And I get 9 over 2 theta minus sine theta cosine theta plus c. Okay, now, what do I do with this? Well, I know that I got to get rid of the theta because the original function here, the independent variable, is x. I did a substitution to make this easier to work with, but I've got to go back and put this in terms of x. So, sine theta and cosine theta, well, what I'm going to do with this, I'm going to draw that triangle again. Okay, now remember, when I made my substitution here, I'll go back up to it. My substitution was here that x was equal to 3 sine theta, which means sine of theta is x over 3. So x over 3. And then down here, this is going to become the square root of 9 minus x squared. So this is the triangle that I'm using to find the integral here. So I can use this to help reinterpret what these trig functions are. So this is going to be 9 over 2. I'm going to leave the theta alone just for a second. And what I'm going to do is I'm going to come over here and what is the sine of theta? Okay, well, sine of theta, I mean, I already knew this from the beginning. That's x over 3. The cosine of theta is going to be the square root of 9 minus x squared over 3 with a plus c on the outside. Okay, so what's theta? How do I work with theta? Well, I got to go way back up to here. And actually, maybe what we'll do is we'll bring this down here. If x is equal to 3 sine theta, then I know the sine of theta is equal to x over 3. And therefore, as a result, theta is the inverse sine of x over 3. That's what theta is. So, again, I'm doing this question so that you can see this, that you get prepared for that. Okay, that means that that theta right there gets replaced with the inverse sine of x over 3. Okay? Now, I should probably expand that out a little bit because things do simplify a little bit, but what's interesting to note is that this piece right here, this little inverse trig function, is part of the solution to this integral. I can't actually go back and get rid of it like I did with some of the other trig here. I'm stuck with that. So the answer to this problem has this inverse trig function in it, which is actually really kind of neat. So this is 9 over 2 multiplied by the inverse sine of x over 3. And then when I distribute the 9 over 2 through, the 9 is going to cancel with the product of the 3's down there. And I'm going to be left with the negative x over 2 square root of 9 minus x squared. And at the very end, plus c. Can't forget about the arbitrary constant. Okay. So I hope that clarifies trigonometric substitution, or at least gives you an idea of how you would do it. Notice that the questions tend to be a little bit more involved. This is some of the more involved work that I've done on a problem, and you've seen that on a couple of these problems already. But I promise you it actually does make things easier to use trig substitution.